Another complicating factor we talked about this already, the levees, that levees can fail. They can be exceeded and overtopped, but there's also a chance that the levee fails to perform before the design elevation. And so there's some uncertainty in terms of the levee performance and how that integrates into the flood risk analysis. And so how we deal with that is development of levee fragility curves. So relationships of channel water surface elevation to the probability that the levee fails to protect, or the probability the levee fails, or like to say the probability that the interior gets wet given that water surface elevation. And this is developed by a lot of work by the geotechnical engineers. And so the state of California, the Corps, has gone through and drilled a lot of holes throughout the levees, done a lot of field investigations to look at the properties of the levees, and then also various paper studies, and developed detailed water surface elevation, probability of failure relationships, levee fragility curves for all those index points throughout the Sacramento basin. And so we talked about there being about 100 index points for the basin right now. And so there's levee fragility curves for various conditions for all those points. And then this is something that we can feed directly into the flood risk analysis model. Another part that makes the analysis difficult, again, back to the levees, is how do we account for what goes on upstream? And so let me give you an example. If we're down here at, let's just start at index point 1, we know that the amount of water we have to, like I mentioned, develop an unregulated to regulated relationship. We've got to route our water to the index point, and we want to develop a regulated flow frequency curve that represents the flow at index point 1. It has its difficulties, but straightforward. As we get further down through the system, say we're going down to index point 2, 3, or index point 4, it becomes a little bit more complex, because what we have to look at is not just how the system performed, but we have to consider that part of the levees. What happened? Given that we were interested in the most likely condition, what do we assume happened at index point 1, 2, 3, all these other levees upstream to develop that needed regulated flow frequency curve, stage frequency curve? So in other words, when we have our complex system and we're using FDA, but we do have system models, what are we going to assume for upstream levee failure scenarios? So what can we do? How do we address that problem, knowing we want the most likely condition, and that's what we're really after in our flood risk analysis. So talk a little bit about some of the solutions. I mean, I think you can ignore it and hope it goes away. I don't think that's going to work, but I guess you could always try it. I think folks know that it is a really big factor in the analysis and the system that we want to make sure we're capturing what that most likely condition is. And so ignoring it just isn't an option. One option is to treat it like FEMA did before, and just essentially assume the levee doesn't fail, kind of a worst case scenario. Levees don't fail upstream, but that really defeats the purpose of doing a flood risk analysis to begin with. And again, we're not really using the most likely condition. Another option is to kind of use our frequency-based storms, but follow kind of a complete enumeration. So basically, we're considering all possible combinations of upstream levee failures. Sometimes it fails at 1, sometimes it fails at 1 and 2, and kind of go through and just go through and do all this work and try to fold all those calculations into the analysis. Another option is to kind of do more of a selective enumeration. This is where we kind of identify some of the cases that we think are most likely to occur, some of the most likely scenarios in terms of upstream levee failure, and simulate those and fold that into the risk analysis. We can do something more of like integrated sampling. This is similar to where HEC Watt's going. And so we're we have tightly integrated the hydrology, the hydraulics, the risk analysis. And so we're going through various sampling and explicitly putting in the levee fragility curves, for example, and computing flood risk. And then another option is to do something more like a period record analysis. So ideally, if we had 1,000 years of record, we could just kind of sum up the damage every year and get that average and give our expected annual damage. So that's kind of a range of possible solutions that have been out there, ignoring it to doing very detailed, sophisticated modeling. Like I said, the complete enumeration, like I said, that's going through and developing all these different scenarios, all these combinations. I kind of hinted why that doesn't work is probably just the sheer volume of runs you have to look at. I had some statistics that, if you had 20 impact areas, index points, 8 events, 2 different storm centerings that you looked at, you could easily get to about 16 million iterations. Assuming your model is fast enough, and it takes a lot longer than this, but 5 minutes a run, you're talking about 160 years of computations. And so, that's not feasible. Again, we talk about HEC-WAD and going forward, I think there's a ways around that. But back when we first faced this, okay, that's we're not going to do that. So what we did do was more of the frequency-based storm analysis with selective enumeration. So we gathered a group of experts in the system, gave them the information they needed to know. For the analysis, we looked at folks that had a long experience with the basin, been through a lot of different floods, very aware of the current status of the levees and improvements, and asked the panel, give us some of the combinations that you think are most likely. And we developed through that process about 13 different scenarios that of various combinations of flows and levee failures, simulated that through the system, and developed essentially computed flood risk, assuming each of those scenarios realize themselves. And so we ran FDA for each of the scenarios and then analyzed those results. And so we computed EAD, assuming, for example, there's some risk that some chance that no levee fails, but also that maybe 4 or 5 fail in this system or a couple fail in this other system. And just to give a flavor of the results, then when we did that, this is a stage frequency curve that we developed at a downstream point near the Sacramento area, and just gives you a range of what types of differences in water surface elevation we can see because of the upstream levee failure scenarios. And so let's take the 1%, the 100-year stage, that depending on what the levees failed or not, or what combination, we're talking anything from a elevation 37 to about 39, so about a 2-foot difference. And when you look at that, what that translates into annual exceedance probability, expected annual damage, a really big difference. And so we're looking at an expected annual damage anywhere from 10 million to 3 million based on what happens upstream. And so, I make this point to show that it really is important to consider that upstream levee failure and to fold into the analysis and to account for it in some way. And we don't want to just ignore it because we can really overstate the flood risk or understate it. Why it's really hard to do is we're also looking for is the most likely scenario, the most likely future condition scenario. And it's interesting that within the Central Valley, there's been various lawsuits after the 1986 event, a famous Paterno versus State of California. And essentially the state has been found liable for the levee failure and not maintaining those levees. And so that's, I mentioned the state's Central Valley Flood Protection Plan effort in their periodic updates and the updated flood risk, and really to be proactive on that. This was one of the big drivers of that effort, of why the state had to invest in that, and it continues to. So now you kind of think, well, if the state's more actively looking at this, trying to find fundings, it'd be held liable if those levees fail. What do you want to assume? So do we want to assume that the levees are going to be fixed to design profile, or again, still represent the most likely case at any given point in time. So again, it's not a clear-cut answer, but something that as we go through the studies and we want to continue to watch and consider the current state of the levees and what we think the most likely future condition is going to be.